All right, so let's continue with our discussions on data in materials informatics. And after going over just a brief background of how discoveries are done and how data driven methods can accelerate those discoveries and what type of data is needed, let's talk a little bit about the different types of formats for the data sets. Now, most of the materials data that you will come across will be stored either in XLSX format or a CSV format or a JSON format. So JSON actually it is just short for what we call a JavaScript object notation, and the syntax for this is quite similar to your standard Java. You can kind of think of JSON files as something which is very similar to your Python dictionary, and the way you read the file is no different from how you read a CSV file or XLSX file. You just import the module for JSON and then you just read it, and that would be it. So essentially these are the steps. You want to go ahead and import JSON, you want to open your data file and then load it, and after you've loaded it you want to write it into a pandas data frame. And then after that, if you want to do any modifications with the data set, you can go ahead, do whatever operations you want with the pandas data frame, and then what you do is you simply write the pandas back data frame back as a JSON file. So the advantage with JSON, just because of the type of syntax it has got, is that it will permit hierarchical and relational storage of data. So what do we mean by that? This is just an example. So for instance, if I am creating a database of different elements, and let's say I've got a couple of elements like aluminum and copper, and I want to store a bunch of things in there, like the melting temperature in degree centigrade, the valence, and so on. So what I can do is I can create an hierarchy where at my first level of hierarchy, I have the name of the element which is there. So let's say that would be aluminum or that could be copper. And then in my second level in that hierarchy, I can start saving different properties or features for that material. So this is the main advantage of the JSON dataset. By and large, if you look at the different aspects of JSON and CSV, you will see that JSON has a larger file size necessitated by the way the data is stored in there. Couple of major advantages for JSON is that it will integrate nicely with API, and it allows for hierarchical and relational storage of data, which you will not get in CSV. In case of CSV, what you have is a tabular data and not a hierarchical data. The CSV although has a different advantage in the sense that it's a much more compact file size, and of course, the issue with CSV is you cannot integrate it as easily as you can for the JSON databases, and they're not quite as scalable. So for the purpose of this course, if you want to write any initial short codes related to materials informatics, I would suggest going ahead with the CSV format. It's perfectly fine for this course. And in fact, for many of the research applications, it'll work. But the JSON format is really useful if you need to upload the data to any of the API accessible databases, which we are going to talk about, and if you really need that hierarchical and relational features of data storage. Now, once you upload the data or once you prepare your data set, how do you actually go ahead and access the different data sets? So for that, there's one very useful tool available called PyMatGen. So PyMatGen is just short for Python Materials Genomics. And I think by this time, since hopefully you have already started doing some of the machine learning work from the first 20 lectures of the course, you would have already downloaded the Conda environment. And so once your Conda environment is downloaded, you can simply pip install PyMatGen. So there are lots of advantages with PyMatGen, but the one which I want to emphasize right now, and the others we can talk about later, but the one that I really want to emphasize right now is that once you install PyMatGen, you will be able to use the REST API which has been developed by the materials project. And this is going to allow you to access many different types of database. So you can simply go to pymatgen.org if you want to look at the other details and other features of PyMatGen. In fact, even beyond using the REST API, there are lots of other things in PyMatGen which would be really useful for a material scientist, especially if you're in the computational domain. Okay, so we now have a tool in which we can import data from different databases. That's your REST API. So once you have PyMergen, you can do that. But then now let's take a look at what the dataset should actually include. So when you are creating a dataset, of course, especially for the purpose of training your code, you want to have one set of input values, right? So when you want to make any predictions, you will be giving this type of values, and based on this type of input, the predictions will be made. After you provide the input, you need to have a set of feature values. And what we are trying to do over here is we are trying to featureize the problem. These features are essentially descriptors of the materials and the processes which we are trying to model using our materials informatics approach. And these features can be something you can enter directly. Usually that has a challenge, because that would mean if you want to go with any arbitrary input, you need a huge repository of these features. So a lot of these features are actually things that you can calculate. So for instance, suppose you want to predict the phase stability of different materials. We know that because of this Hume-Rothery type of rules, the valence electron concentration becomes an important parameter. So the valence electron concentration is something that you can compute based on the composition of the material. And therefore, if your input is the composition of the material, the valence electron concentration is a feature that gets automatically calculated when you mesh out your data set. So you can have features which you input, but you will find that in a lot of the cases, we will be using feature values which are actually computed in the database. So once you have your input and once you have your way of featureizing the problem by including the features, the final set of data that will be present there are the target values. So these target values are really the properties that you are trying to predict, and this combination of the input values, the feature values, and the target values will allow you to train your program. Okay, so by and large, whatever you are trying to predict, that comes in this target values. Okay, so this is how the data set should look like. We also talked a little bit about how can you access data. Now the question is, from where are you going to access data in order to create the type of data sets that we just talked about? And for that, I just want to briefly go over a number of data repositories that are available which can be used. So one of the most commonly used databases which you can access online is AFlow. So AFlow basically stands for Automatic Flow for Materials Discovery, and this is an excellent database which has a vast repository of crystal structures, ab initio thermodynamic properties, and different types of elastic properties. And this is one database which you can easily access with the REST API that we talked about. So in this AFlow database, you will find a huge amount of information related to the quantum properties, the thermal properties, structural and elastic properties. However, these are primarily the properties of different types of inorganic compounds. So if you're really looking at the properties of alloys, you can look at other options. But if you're looking at properties of different types of inorganic compounds and intermetallics, this is actually a pretty good database that you can access. Another very interesting database is OQMD. So OQMD is maintained by Chris Wolverton's group. And this is again another dataset which contains information on crystal structures, phase diagrams, electronic structures, and so on and so forth. So there's a large number of quantum materials for which all of these things have been calculated for you. And so if you need to access those type of data, this is one database which would be really useful. So you can search, you can query, you can create phase diagrams, so you can determine the electronic structures calculations and the ground state compositions. You can visualize the crystal structures, and all of this is accessible using the REST API that we just talked about. So these are big databases, and you can all access them using the REST API. So I hope you understand that I really expect you guys to download and install PyMergen and start using the REST API. That's going to really cut down the amount of work you would have to do in order to construct databases. The third one I wanted to talk about is another major open source database that's available out there, and this is the Materials Project. This has been going on for a long time, And this is something which is maintained by Gerben Cedar and Kristen Person. And here, again, you will get a lot of information related to the phases, to the crystal structures, the pore bed diagrams, reactions. Lot of info will be there on battery related materials. And as you can see on the slide, there's a large number of database entries. You will have data related to XAF, ZANES, density of states, band structures, and so on and so forth. And of course, this is the one where they actually started making data sets which would be accessible with the REST API. So again, pulling in data from this type of data set is going to be relatively easy. And that's why these data sets, these open source databases are so important. Now, all you basically have to do is you need to import the API, the MP rester function. And once you have the MP rester function imported in your code, you can simply start querying and go ahead and get the data. So I would urge you to actually visit this website, materialsproject.org, and look into how you can actually integrate this MP rester API in order to pull the data from these databases and then import it onto your code. In addition to these three big databases, there's lots of other useful information that's available online. I'm going to go through them very quickly, and so that you have an idea. I'm not going to get into the details of all of them, but you have a computational materials repository page, which is maintained by the Denmark Technical University. And here you have links for lots of different types of data which you can look up. So I really urge you to visit this particular website that I have cited over here, and you will find the links to a vast assortment of materials data. Mostly this would be great if you're looking at the physical and the chemical properties. Again, not so much for the metallic alloys, but really great if you're wanting to look at quantum properties and different types of compounds and so on. Another one I wanted to talk about is the Open Materials Database, and this is maintained out of Sweden. And there are really two groups which contribute to this. There's a group from the Linköping University, and there's a group from the University of Basel. And again, you have a large variety of data that's available. This Open Materials Database also has their own high throughput tool, which they call the HTTK. And you can use that tool in order to pull data and analyze results and so on from this particular website. If you are looking for data which is generated using atomistic modeling, AIIDA is another interesting website to look at. So this IDA website will provide you with automated workflows. And this is really great if you are looking to do some kind of molecular dynamics type of work or atomistic modeling type of work in order to generate the data which you can then use for your machine learning this machine learning journey. So for this, you can visit www.ida.net, and this is another of these useful sites which I just wanted to mention. Then you have another site called ELSA, and this one is dedicated to electronic structure calculations. So ELSA actually stands for Electronic Structure Database, and again this is another database which is maintained out of Sweden. In addition to this smaller databases which are maintained by different groups and different universities, nowadays there's also a consortium type of approach which is being taken to deal with large materials informatics type of problem. And so the European Union has taken multiple such initiatives, and I'm just going to list a couple of them. So the first one is FAIRMAT. So FAIRMAT, basically it's an abbreviation which stands for Findable, Accessible, Interpolable and Reusable Data. And this FAIRMAT database is an excellent repository if you are looking at materials from a condensed matter physics type of perspective, or like a chemical physics type of perspective. And you will get a lot of information related to the structure in terms of the coordination numbers, the crystal coordination, different types of synthesis that has been done, and so on. So this FAIRMAT is another interesting consortium which is useful data infrastructure that is available out there. And then closely related to that is a second EU initiative, which is called NOMAD. So NOMAD stands for Novel Materials Discovery, and this is again machine learning enabled materials discovery type of platform. And you can also get a good amount of data sets from this NOMAD website. Now, in addition to having the different types of data sets, you can also participate in some of the lecture series that they conduct now and then. Coming back to some of the more traditional databases, because you may not be able to find everything you need in the other online databases that we talked about, the ones you can access very easily with API. So that's why I wanted to bring up some of this more traditional databases. So the first one we talk about is COD, or the Crystallography Open Database. And this is an excellent resource if you are trying to look up the crystal structures of different phases. So this is a site which is very easy to browse. This is a site which you can actually query the type of compounds that you are wanting to look at simply by specifying the elements that are present in the compound. And then it gives you a tabular list of all the different compounds for which it has the data. And so you can start pulling out the data from there and use it for your further applications in machine learning. Now, the one thing I really wanted to emphasize is, if you look at the quality of data which you will normally find in this field of material science, you'll find that this data has been represented in diverse manner. And different researchers have, when they have done the experiments and gathered the data, they may have actually shown this data and published this data in slightly different format. However, crystallography is one field where you have a lot of structure that was already built in earlier. And so the crystallography data is uploaded and stored in form of very well-structured files known as CIF files. So CIF file is short for crystallographic information file. So this is an aberration in the sense that this is one of the areas of material science and engineering where the data is extremely well structured. Yet another open source data repository I wanted to talk about was the NIST Materials Data Repository. So if you go to materialsdata.nist.gov, you will find lots of different types of data repository. So all you need to do is pull up the drop down menu, and you will find that you've got data for additive manufacturing. You'll have data related to different computational information, data related to freeze casting, and so on and so forth. So a large and diverse variety of databases are available in the NIST Materials Data Repository, including things related to phase equilibria and diffusion, the structural properties of materials, and so on. So a lot of the databases that we had talked about earlier were catering mainly to this inorganic compounds and intermetallics, whereas this NIST type of database, you will also have a lot of information related to alloys. So if you are a metallurgist and looking at this, this might be a very useful database to look at. In addition to the NIST Materials Data Repository, a lot of work has been going on in the United States on doing this data-driven discovery of materials. And a lot of companies have actually jumped into this space. And one of them happens to be Citrine. So if you go to the Citrine website, once again, you will find a number of this success stories related to materials informatics. And some of the data sets curated by Citrine has also been uploaded online. So this is yet another place where you can look into materials data. One of the interesting features of the Citrine website is they also present some case studies in doing materials informatics. And so for somebody who is looking to get into this field of materials informatics, going through these case studies can actually be rather informative. And I would strongly urge you to look into this. Now, one can go on and on about a whole lot of databases which are available online. But what I thought I would do is I would just provide some links to different GitHubs, which provides a lot of this information in very condensed manner. In some of these cases, they also annotate the information and provide their comments on what are the different strengths and weaknesses of different databases and so on. So what I would suggest you to do is, at this point, you can pause this video and then go ahead and explore these links and see from where you can find the type of data that you really want. Now, in addition to that, whatever online repositories you have got, the traditional sources of data would be different materials journals. And nowadays, you also have different serial titles like Data in Brief and Scientific Data, which is intended only for uploading different types of data repositories. So this is another set of resources that you can search in order to find the type of data that you really need. Now, few things I will want to point out, that sometimes the experimental materials data is still going to be very difficult to find. And so that's why you will need to do some sort of combinatorial experiments. The caveat there in this combinatorial experiments is many times these experiments will be performed in non-equilibrium conditions. And therefore, when you try to extrapolate that data into near equilibrium processes, that might be a little bit problematic. Another thing I'll just want to state upfront is a lot of the data that we'll work with would be thermodynamic data or ab initio data. And as a request, I'll just say that if you're going to publish papers, it would be great if you can upload the codes in GitHub and upload your databases, because that really allows the next generation of materials informatics researchers to find information very easily and so on. Now, the final thing that I'm going to talk about when we discuss about data and materials is recent development, which is a tool called the MatMiner. And this is something which is maintained by the Lawrence Berkeley National Laboratory. So this MatMiner has a lot of functionalities. You can do data retrieval from materials projects, Citrine, and other types of databases. There is a feature which allows you to do the feature extraction. You can do a lot of visualization using the inbuilt libraries in MatMiner, and then you can also do machine learning using different types of libraries such as scikit-learn and Keras and so on. So again, this is something which is very easy to install, and you can, if you have your Conda environment, you can simply do a pip install for MatMiner. And I'm just putting up the link if you want to go through the documentation. I would strongly urge you to explore this tool. This is also a very useful tool for people interested in materials informatics. And if you visit the MatMiner website, they actually have a very nicely written up documentation which tells you about all the different features of this particular tool. In addition to visiting the website, I would also urge you to look at the original paper that was published related to MatMiner. As you can see, this was a pretty large team of scientists that were working on this project. And so just do yourself a favor, go through the paper, see what MatMiner is all about, and then you can start using the MatMiner. How you will use it, what you expect to get out of it, let me just show you via some short examples. So essentially what you want to do is you want to use MatMiner to actually mine online the different data sets that are available. So you have to write a proper query about what type of data sets you are looking at, and then using MatMiner you will sort of start mining the information online. So for instance, I'm just giving you an example of some of the data sets that MatMiner is able to find. So the Boltzmann trap data set is something which is extracted from this materials project database. And this is primarily based on the density functional theory type of calculations. Then the second one is really something which is a database of super hard materials. The third one deals with perovskites and so on. So as long as you are able to query properly, MatMiner will be able to find an array of databases as long as they have been uploaded in some of these major open source databases. Now here, what I would just like to illustrate how you are going to retrieve the data from different places. So all you need to do is you have to import this MatMiner's data retrieval function, and after that you start putting whatever type of criteria you want. So here the example is that of datasets which contain compounds and alloys containing silicon, and what we are trying to find now is the band gap. So as you would have guessed, this is something which would be really useful if you want to do some materials informatics related to semiconductor. Okay, so these are the primary tools that I just wanted to present. So in some sense, when I talked about this data in materials informatics, this is really more of an introductory overview as to what type of data is needed, how you are going to store the data, what are the different types of data sets in terms of how the data is stored. I also wanted to bring up lots of examples of open source databases because that is something which is going to be really useful, as well as different tools that you can use in order to retrieve the data from there, including the MP-REST algorithm, as well as mining the data in terms of using MatMiner. So with that, we are going to stop here for today and we'll move forward again tomorrow.